Picture a crowded animal rescue center on a Tuesday morning. 3 dogs arrive needing emergency surgery. 5 fosters are dropping off litters of kittens, and 20 volunteers are attempting to coordinate their afternoon shifts, all happening simultaneously in the exact same physical space. If you look closely, this operational chaos poses a strict, high-stakes, parallel processing logistics problem. The core constraint driving this problem is simple. A single physical entity, a rescued dog, must exist inside multiple, overlapping workflows at the exact same time. It needs medical clearance, requires behavioral evaluation, and spatial housing simultaneously. Translating this physical overlap into functional software means creating a digital model where every real-world event has a corresponding logical state. The Animal Rescue Management System Comprehensive Report provides the precise architectural blueprint for solving this specific domain problem. To understand how systems engineers tame this level of daily operational friction, we have to reconstruct the system's architecture from first principles. That means starting all the way down at the data bedrock. The system must reconcile 3 distinct domains: veterinary care, volunteer logistics, and adoption workflows. The survival of the entire rescue operation relies entirely on the system's ability to prevent state transition collisions across these 3 distinct areas. Look at this diagram. Our rebuild begins with the animal table. ID and species are static, immutable data points that never change. By contrast, the status attribute is highly volatile, constantly shifting as the animal moves from intake to quarantine to available. This specific attribute functions as the foundational finite state machine constraint for the entire backend architecture. A finite state machine enforces strict algorithmic rules. A dog cannot transition to the available state without first satisfying the dependency state of clearing quarantine. A non-relational database or a simple flat file structure would instantly buckle under these operational rules, allowing impossible states, like adopting out a dog still in surgery, to be logged. However, the animal table alone is useless if we do not mathematically map its interactions with external constraints. The first major external constraint is the medical bay, where specialized veterinary interventions happen on highly unpredictable schedules. A robust relational schema must enforce hard constraints on the entity states at the database level before any secondary logistical operations can even be considered by the business logic layer above it. This expanded diagram illustrates the scaling problem. One animal requires multiple vet visits over time, while one veterinarian treats multiple different animals simultaneously. As you can see, linking base directly creates a confusing, overlapping web. This is a classic many-to-many cardinality conflict, and it directly threatens the mathematical normalization of our database. To resolve this, system architects engineered a junction table. We place a new entity called treatment logs centrally between them, linking the tables using foreign keys. Now, a single data entry in the treatment logs table simultaneously updates the veterinarian's operational schedule and the individual animal's medical history, entirely avoiding data duplication. The schema continues expanding to handle the second major operational domain, the volunteer and foster logistics module. Volunteers require very specific schema mapping. The system must continuously track their shifting spatial capacity at home, alongside their fixed licensing permissions, which dictate the types of animals they are legally allowed to handle. The logic matches an animal's specific behavioral requirement level, pulled directly from that core animal table, to the individual foster's specific licensing level. These junction tables and strict foreign key relationships act as the mathematical glue. They prevent anomaly-driven operational failures, like double booking a single vet for 2 surgeries, or placing a dangerous animal with an unlicensed foster family. Look at this architectural block diagram. It shows how the system operationalizes raw data into actionable workflows using 3 distinct tiers. Notice the strict boundary lines. This implements separation of concerns, ensuring that data flow is highly controlled between layers. Focus entirely on the middle tier, the business logic layer. This is where the operational use cases from the report are converted into strict executable algorithms. Consider a high-risk operational scenario. A user at the front desk attempts to process a final adoption for an animal that is currently flagged in medical isolation. Here is the precise API interaction that prevents disaster. The adoption module pings the medical module before allowing the transaction to commit, resulting in a stark denied signal. This modular architecture prevents catastrophic overrides. The user interface simply cannot force an adoption transaction if the underlying medical state machine rejects it. The strict modularity also means developers can update the medical module's quarantine protocols on the fly without having to rewrite any adoption module logic. In life and death logistics, cross-module validation rules are where abstract architectural boundaries literally enforce physical safety protocols on the ground. This diagram visualizes the complete interconnected system, orchestrating a full lifecycle event. Watch as a single data packet successfully traverses up from the data layer, is validated by the business logic layer, and populates the user dashboard. The system's speed and reliability are a direct result of precise data normalization. By decoupling the modules, the architecture ensures that a change in one domain never destabilizes the others. Think back to that initial physical chaos of the rescue environment, the overlapping medical emergencies, complex foster placements, and overlapping volunteer shifts. The software system acts as a digital funnel, forcing those entirely unpredictable physical events to conform to predictable mathematical states. The report demonstrates how these structural principles solve high-friction resource management problems, where data integrity is essential to safety. This specific approach creates an unyielding logical framework capable of sustaining the unpredictable demands of the real world.